is not very visible. He's remote. And he's Aldo Serenelli from the Institute of Space Science, and he's going to give us a review about solar models and neutrinos. Whenever you want, it's your turn. You go.
Okay, thank you very much. First of all, I appreciate the invitation by the organizers and the big efforts they did so I could be in South Africa today, but unfortunately I had to cancel my trip, and I apologize to them and to all the audience for this. So yeah, my talk will be on solar models and neutrinos. I'll try to give you an update of the situation at the moment, okay? So let me first quickly start by showing you this famous comparison between experiments and models, where you can see in blue experimental results from the old chlorine, water, gallium, heavy water, and then the Borexino results in blue, whereas the others are the results from standard solar models. I guess you all know this very well. Of course, this does not include oscillations. Now, first part of the talk, I will discuss a little bit the situation of how well solar neutrino experiments are able to constrain solar models in a completely model-independent way, right? And so the big advancement here came with Borexino measurement of beryllium-7, a very precise measurement that allowed them to reconstruct the solar fluxes pretty well, right? So this was done by Bergstrom in 2016. What I'm showing here is the distributions of posterior distributions of all solar neutrino fluxes that are obtained using only experimental results from all neutrino experiments, and the oscillation parameters are also free parameters in the analysis. So what I'm most interested here is just to show you the result that is highlighted there in the box, where the solar luminosity can be explained by nuclear reactions as inferred from neutrino fluxes. As you can see, they are coming 1.03 contribution from the PP chain reactions, and a tiny or even consistent with 0 contribution from CNO on the right. So this is a very good agreement with between the experimental results and solar models, or not really solar models, but let me say with the observed solar luminosity. As I said, this is completely model independent. You can see the uncertainties are at 1 sigma about 8% or so, right? But this is still a very nice result, which goes back to the original question posed Castelmore almost 70 years ago now. How does the sun shine? Okay. Now a bit more recent, but then we will have a full talk on Borexino results later in this session. Okay, Borexino produced a very nice measurement of all neutrino fluxes coming from the PP chains, except HEP. But okay, HEP does not matter for our discussion here today. And so you have here an update of the plot on the right-hand side. And the nice thing here is, or the very big advancement, I would say, is the possibility of now measuring PP flux directly, not just extracting it as a residual from the gallium experiment. Right? Okay, the experimental result is still about 8-9% for PP, but still this is an impressive achievement by Borexino. Right? As I said, we'll have this talk later on about this. So let me just recap about the origin of solar luminosity. A purely experimental result, going back to Bergstrom that I showed before. This is 1.04 for the total nuclear energy being generated in the PP chain plus CNO. And if you use only Borexino results, this is still very much consistent, within 1% the central value with a 1 sigma uncertainty of about 10% or so. So this is result from the Borexino Nature paper 2019, where the difference with the Bergstrom result, I would say, is that neutrino oscillation parameters are taken from Esteban 2017 and not part of the fit. Okay, but you see, this is a very nice agreement, right? So now we go a little bit to solar models, standard solar models in particular. So according to standard theory, the origin of the solar luminosity should have basically two different sources. On the one hand, you can see here, the first term here is the nuclear reaction energy, of course, accounting for the energy that is being carried away by neutrinos. Then there's the second term, which we usually call in stellar physics gravothermal energy, which is related to compression and expansion. Can be either positive or negative, depending on the region of the star you're looking at. Right. Now this second term, now according to solar models, it's really negligible. It's smaller than maybe parting 10 to the 3 or even smaller compared to nuclear energy. So to very good approximation, we have the very standard result that basically all solar luminosity should come from nuclear reactions. Okay, so this is what we are in fact testing using experimental results from neutrinos, right? Which is this results I showed before. So this is a very nice support to the idea of stellar evolution. It is for low mass stars, of which the sun is, of course, a primary example. Right? Now we can go to non-standard solar models, and in particular, this is of some interest for exotic channels of production or of energy inside the sun or inside other stars. And now in this case, we add an additional term, which can be either a source or a sink of energy. For example, a freely escaping particle like axions would be a sink of energy. If you have dark matter which self-annihilates, then this is an energy source. And then in this case, well, of course, the two contributions from nuclear energy and the dark energy should amount to the observed solar luminosity. So in this case, we have this inequality here. So neutrino results can help us test this. We have, again, the same results as before. And again, we have a nice result here, but still it's a bit of a problem. The 1 sigma uncertainties we have here, which are of the order of 7 to 10%, or so, depending on the analysis you do on the experimental data. So this is a nice test of non-standard solar models, but it's still not very constraining, because the 1 sigma uncertainty is pretty large. So from this point of view, it's a great achievement, the PP measurement from Borexino, but still, if we want to really push these limits here, a much better measurement of PP flux would be required. And a sensible goal, which I will justify in the next slide, is that about a 1% measurement should be desirable for the PP neutrinos. Now, this is, of course, difficult, but okay, life's not always easy. So why do I mention this 1%? Because, of course, so far we discussed only completely solar model independent limits, but when you add some trust in solar models to the mix, then you can get much more constraining limits than purely experimental, right? And this is just to show you an example. This is from a paper a few years back for a former student. Here you can see on the x-axis the amount of the fraction of energy being lost from the sun through a dark channel, either axions, hidden photons, doesn't really matter. And you can see on the y-axis the sigma level at which you can let's say, rule out that energy loss, right? And so here you can see that, for example, for actions, which is the worst of the two cases, a 3% energy loss through actions can be already ruled out at the 3 sigma level if you use solar models, meaning if you compare directly the neutrino fluxes in the models with the neutrino fluxes measured by experiments, and if you also use helioseismic constraints of solar interior. Right? So this is much more constraining than the purely model-independent constraints. So really, experimentally, it would be excellent to really push the uncertainties lower. Because of course, we would like to be as model-independent as possible. Now, there are other cases where this solar luminosity constraint, in a sense, does not really apply, and you can have, for example, the case of asymmetric dark matter, where you don't have any annihilation, and it's just particles inside of the sun affecting energy transport, but without really affecting the overall energy budget. And so your integral here is 0, and so here you are forced to rely on models, right? But overall, my idea here is try to emphasize the fact that we still need to have very high quality solar models, in particular for these applications, but for others as well. Right? So this brings me now to discuss a bit on standard solar models in particular. Right? So we have two basic, let's say, type of quantities here. Right? So on the left, you have constraints that we apply to the models. Right? In particular, in a standard solar model, we assume that the constancy of solar mass, meaning that the amount of mass that is lost through winds or by transformation of mass into energy is very small. It's a very small fraction of the solar mass through the whole life of the sun up to present age. And then on the right, on black there as well, you see the equations of structure and evolution. These two quantities basically define what the standard solar model is, what physics I can put in my model, and in particular that there's no mass loss there, right? But then you have additional constraints like the age, the radius, the solar luminosity, the surface composition that's measured through spectroscopy and other techniques. And then the input, the microscopic physics that we use in the model, equation of Tate, nuclear reaction rates, radiative opacities, and other physics, and how you model this, right? Now, out of this, of course, the critical issue has been now for quite a long time, the surface composition, and this has put radiative opacities in the highlight as well. So I will discuss a little bit about this. Okay. So first, the solar composition, as I said, it's a constraint that you apply to the models because your models cannot predict what the surface composition is today. You just use this as a constraint to infer the initial composition of the sun. Okay, and the two big paradigms here have been what we now call the high metallicity solution, which is identified here in blue, and the low metallicity solution, which is the one identified in red. And you see, relative to the high metallicity, which is in blue, for each individual element, okay, for the most relevant ones at least, you can see the fractional difference between the two. Right? And so this large reduction in the low metallicity solution has come in the last 15 years or so, because better techniques, basically, for analyzing solar spectra have become available, both from the point of view of simulation of the solar atmosphere, but also the detailed atomic physics that goes into spectral analysis. And it's a large reduction, of course, especially for volatile elements, so CNO and neon here. Okay. Now, this, of course, has a large impact in solar models that has been discussed why in the literature a lot. And the influence comes basically because metals determine the interior opacity, or the radiative opacity in the solar interior. Okay, and so here I just try to illustrate this. So here you have three panels. It's in the center of the sun on the left, in an intermediate region, so about solar radius 0.4, as you can see here. Okay. And then in the outer part of the radiative interior at radius 0.7, This is all normalized to 1. And you see the contribution to opacity from individual metals, plus hydrogen and helium. And you see, of course, in particular here, that the oxygen, neon, iron, they play a very, very important role in the opacity, okay? Now, why does the opacity matter? Because the temperature gradient that you can see up here is basically proportional to the opacity that you have in the interior. So by changing the amount of metals you have, you will modify the opacity, and through this equation here, you will modify the temperature stratification that you have in your model, okay? And of course, lower metals imply lower opacities, okay? And this has a strong impact on the properties of the solar models, and this has been, as usual, exemplified here by showing the sunspeed profiles. Okay, the difference between the sunspeed in the sun and in the model. Okay, so 0 here is a perfect match. And you can see the high metallicity results in blue, the low metallicity results in red, plus uncertainties in the shaded regions. And you can see, of course, what most of you know, probably, that the low metallicity solution is quite bad compared to the older one. Paradoxically, one could say, this is based on much better spectroscopic techniques, right? So this has been kind of a conundrum for the last, as I said, 15 years or so, and really no neat solution in sight yet, okay? And the big problem is that metals only affect seismic properties basically through temperature gradient, right? So we have this degeneracy between metals and opacities that has been proved so far very difficult to disentangle, right? And solar neutrinos so far are not very useful in this regard, okay? Now you can see here on the left the experimental results for beryllium-7 and boron-8 on the y-axis, shown here as a cross here, because this is all normalized to experimental results. And you can see the result from the high metallicity solar model and low metallicity here, okay, where the ellipses depict error bars coming only from all ingredients in solar models that affect the core temperature, okay? So nuclear reaction rates are left out in this left panel. And then you can see that the two solar models align very well along a central temperature sequence, which is the dashed line in gray, okay? This means that, okay, the experimental result and the models are very well aligned at temperature sequence. So there's nothing fundamentally wrong, for example, in a nuclear reaction rate, let's say in proton plus beryllium-7 or something like that, okay? But on the other hand, what this means is that the neutrinos coming from the PP chains are not directly sensitive to the composition, but only to the resulting temperature in your model. And how you achieve this temperature, if it's because composition is different or because the opacity is different, we cannot tell from these results, okay? Now, on the right-hand side panel, of course, you add a contribution to errors from nuclear rates, and of course, you inflate the ellipses here because this is now not moving along temperature, core temperature anymore, right? But the bottom line is this one, right? The composition determines the opacity, and the PP chain fluxes are in fact sensitive to the effective opacity you have in the solar interior. That means to the temperature, not really to the composition, not directly to the composition, okay? So here again, the same as with helioseismology, this degeneracy between opacity and composition cannot really be broken by neutrino fluxes coming from the PP chains, okay? Which is not a very pleasant situation, I would say. So let's see about the opacities then, right? So in 2018, what we did is to ask the opposite question. So given the solar neutrino data, given the helioseismic data, can we infer the opacity profile in the sun, right? And so we did this, we tried to include a general description of the intrinsic error to opacities, which is not quantified in the literature, unfortunately. So we did some Gaussian process analysis of this. And the results are summarized in this plot, where you see as the function of temperature on the x-axis, the final opacity we obtain. Okay. And so our result is in blue here. Okay. And all on top of it, you see the opacity of the model with high metallicity, which is the dashed curve here in black, and the low metallicity result here. Okay. So maybe it's not surprising, but what the data is telling us is that the opacity profile in the sun is very similar to the opacity profile in a solar model with high metallicity. Why this is not very surprising is because, of course, the helioseismic data in particular is in much better agreement with high metallicity than with low metallicity. But this result is interesting because it's really, let's say, at least so far, I would say, the best available estimate of the effective opacity in the solar interior inferred from data. Okay. Now, the difference between the two curves here is about something like 18% here at the base of the convective envelope, and then a few percent towards the solar core. Okay. So this is at the moment the situation. Now, should we care about this? Okay, I'm mostly a stellar astrophysicist, and I would say yes, we certainly need to worry about this, mostly because the sun is still really our benchmark for stellar physics. Right? And so here is a nice result done by Christiansen Dalsgaard, where we consider the sun as a star. So we use helioseismology, but only the type of data that is available for other stars. This is called the low degree astroseismology in general, because you only see a few angular degrees in other stars because of cancellation effects. You don't resolve the surface. Okay, and so what you see here is a fit to the solar age using this type of data. And you see GN93 is a high metallicity solution. In dashed vertical lines, you see the solar system age as inferred from meteorites. Okay? And you can see that the high metallicity gives us a very good agreement with the solar age. The difference with what I showed before is that here the solar age is not used as a constraint for the models. Okay, so the minimum here agrees very well with the meteoritic age. And when you go to low metallicity models, you see that this is not the case anymore. So our models are not able to predict an accurate age for the sun if we use low metallicity or low opacities. Okay, and this is a very important fact, because here we have something like 5–6% difference. And of course, we have all these very nice large-scale spectroscopic surveys to model the galaxy, to put accurate ages to exoplanet systems, and all this relies on how good our stellar models are at the end. And you can see that if you take the results from the most advanced spectroscopic analysis, our results are not that good. Okay. But there's more. So here I'm showing very quickly some examples of the Hertzsprung-Russell diagram for models of 0.9 solar masses, 1.5 and 2 here, where I simply changed the opacity by ±5%. And you can see that the location of the stars in the HR diagram changes a lot. Okay. And if you go to the plots on the right-hand side, this is the evolution of the luminosity as a function of age. And here again, you can see that the ages of the stars are very different depending on the metallicity. In fact, the opacity. In fact, a change in opacity propagates almost linearly to the luminosity and therefore to the age of the star, because of this very simple relation from a basic course on stellar physics. Okay, so it really matters that we are able to pin down what the composition and what the correct opacity calculations are for the sun, because this has a very broad impact. Okay. So what is the situation with opacities? Well, we had from Jim Bale in 2015 the only unique measurement of relevant opacities in solar conditions. So this was done in Sandia Lab. So what you can see here in the top plot is an atomic calculation in light blue called OP. This is opacity project. And results from this measurement, this is just iron. Okay, this is not the full solar composition. This is just measurement of the monochromatic opacity of iron. And you can see the experimental results in black. Now, if you see at the y-axis, the difference is basically a factor of 2. Right? So that means that if experimental results are correct, opacity calculations, in light blue, are missing basically a factor of 2 of the opacity in the interior. This is just iron. When you fold this in with the total solar composition, this would not give you this very huge change. This would give you a few percent here, okay, 7% or so. But this is really showing that there's something fishy with the calculations, if the experiment is correct, which is not obvious. But all theoretical calculations, and you can see this in the middle panel, agree with each other extremely well. So at the moment, and this is already almost 5 years old measurement, there has not been a solution to why the quasi-continuum in the opacity calculations here is missing the experimental result by this much. So of course, some people doubt that the experimental result is really robust, but okay, that's an open discussion, okay? And let's say, not very comfortable situation is that all solar and stellar models rely on theoretical calculations only, okay? And the typical scatter, as you can see in this plot, is much smaller than this 18% missing opacity that we have inferred for the solar interior, okay? So, just entering the final part of the presentation, we are interested, and we have been interested for several years now, in finding a nice way of breaking this degeneracy between the opacity and the composition, okay? And of course, the very nice tool we have for this is using the CN cycle, okay? In particular, the neutrinos coming from CN cycle, right? Now, if you have a star that is more massive than the sun, where nuclear generation is dominated by CNO, this would not be a very useful tool. Basically, if you could modify the carbon-nitrogen abundance in that star, you would increase the energy release, okay? But this would produce expansion in the star that would lower the temperature, and so you would have a process that is more or less self-regulated. Okay, so you would not be so sensitive to the CN abundance. But in the sun, fortunately, the CN cycle is really marginal in terms of energetics. So if you do some small changes to the CN cycle in the sun doesn't really notice this. Okay, so there's no feedback on the solar structure basically because it's dominated by PP chains. So in this case, if you increase the CN abundance, there is an increase in energy released by CN, but this is really tiny. So the total energy is really unchanged, okay? And this implies that the fact that the CN elements here are catalyzing the cycle, you will have a linear relation between the CN abundance and the CN energy release, or the CN neutrinos. So this is very useful. So, okay, several years ago with Wick Haxton and Carlos Peñagaray, we did some experiments, numerical experiments, okay? And so you can see here on the y-axis, oxygen 15 normalized to standard model, and on the x-axis, the boron 8. In black, you see results from Monte Carlo simulation that we have done, the scatter of these two results. But if you remove the uncertainty or the variations induced by the CN elements here in blue, and from nuclear reaction rates, the relation between these two fluxes is this red cloud of dots that align very tightly along this line, okay? And what you see in the bottom plot is the residuals here. And you can see the residuals now are 0.3%. This means that the temperature dependence between boron 8 and oxygen 15 is very, very tight, okay? And this can be used to the advantage that if we have a nice determination of boron 8, okay, because it depends so sensitively on temperature, okay, would give us a very good constraint on the core temperature, which would in fact eliminate all the model uncertainties that affect the core temperature, because here we have an experimental measurement of the core temperature, at least of the uncertainty in it, right? And so one can play a little bit with the models and so on, and there's a nice relation that you can build between the CN flux, in this case oxygen 15, but you can do for nitrogen 13 or any combination of the two, the boron 8 here, and then here it's basically the carbon plus nitrogen abundance in the core, okay? And here is the uncertainty budget, okay? So this contribution here is to the temperature, which is very tiny, which is similar to this that you see here, okay? There's a contribution coming from diffusion. We can discuss this if necessary, and 10% uncertainty coming from nuclear reactions, which give us some scatter here, okay? And so what this means is that if now I have a good measurement of boron 8, and then I have a good measurement of oxygen 15, I'm able to extract this quantity here. And this is really independent on opacities, because the uncertainty in opacities is already included in this environmental budget here, which is tiny, okay? So it's really this very nice capability that CN neutrinos will give us, and we hope to hear more, or you hope to hear more later on today, that will give us a very nice handle on the composition and will help us really to break this degeneracy between opacities and composition, right? And keep in mind, if you have a 10% measurement of oxygen 15, for example, in combination with the other errors, you will have something like a 15% uncertainty in the determination of carbon nitrogen in the solar core, which is really comparable to spectroscopy, and I would say probably much less prone to systematic errors. Okay, so this is very nice potential result. Okay, and so what potential application where I mentioned already breaking the degeneracy between opacities and composition. Of course, this would, if at some point, let's say we have confidence on spectroscopic measurement, would give us a measurement of an effective measurement of a mixing process in the sun by comparing core with surface, which is also a very interesting possible result. But then also interestingly, this would give us access to the primordial composition of the solar system. I mean, this is as close as you can get to the primordial composition, because you can see in this plot, this is time evolution. So this is the evolution of the early sun. And in blue, you can see the evolution of the convective envelope. Okay, the star, so the sun starts as a fully convective star. So this is convection from 0 to 1, from the core to the surface. But very quickly, convection recedes towards the surface. Okay, so just in a couple of million years, or even 3 million years here, the convective envelope has receded up to this point. And so this means that the core here becomes isolated from whatever happens to the sun in the surface, okay? And then you preserve here the primordial composition of the protosolar cloud. Okay? And what is shown here with the horizontal lines are the regions in which 95% of the present day oxygen 15 flux is being produced in red, or the addition of nitrogen 13 plus oxygen 15 produced today. Okay? So that means that really, if you measure these fluxes, you would be having access to the composition here, of course, modulo the diffusion in the sun. Okay, but okay, we can get some handle of this eventually. Okay, so this is also a very nice, application. Okay, that we can eventually extract from a CN measurement the CN neutrino measurements. I think with this, I finish my presentation. I don't know how I'm doing with time. Oh, very well, sorry. So let me just give you a very quick conclusion. So as I said, the solar luminosity has nuclear origin. I think this has been proven pretty well so far. The uncertainty is not so good, and this implies that for certain applications, we still need to rely on solar models, maybe not as much as we would like, even more considering this issue with the solar composition, which may make some people uncomfortable in using solar models. Okay. Now there's really a problem with solar abundances, relative opacities. This has been going on for a long time. It really has an impact on solar models. Okay. But this implies that our confidence in stellar models in general is not as good. Okay. So just from this uncertainty, assuming that there's a systematic uncertainty in the age of other stars of the order of 10% or so, it's a sensible idea, and 10% is not very good. Okay, we need to do better. There's really a revolution in observational astronomy, and the stellar models are not really keeping up, in my opinion. Okay. Okay, the temperature problem comes because of this degeneracy with composition and opacity, as I discussed. And of course, CN neutrinos are really a nice way to try to break this degeneracy. Okay, so this is all for me. Thank you.